Yeah, thank you for coming. I'm Alice, and I work on the Android Rust team at Google, where I work on adding Rust to the Linux kernel. So the Linux kernel is famous for being written in C, and C exclusively. No other language is allowed, not even C++. However, in late 2022, Linus Torvalds accepted the addition of Rust as a second language on an experimental basis. Rust for Linux is the project to add support of Rust in the Linux kernel, or to make Rust succeed in the Linux kernel. So I was going to tell you about how adding Rust to the kernel will bring memory safety and modern language features to the kernel, but yesterday, Greg shared this quote on the kernel mailing list, and he really said it better than I ever could. Greg he's a top kernel maintainer. He's seen almost every bug fix and security issue and CV over the past 15 years. And really, as he says, adding Rust will help us eliminate a large swath of bugs and vulnerabilities that are just due to, what did he call it, stupid little corner cases in C. And so by doing this, we eliminate all these vulnerabilities in the kernel. And you have to remember, the kernel is the foundation of not only the World Wide Web, but also 3 billion Android devices. So it's not a trivial place to be. So over the past few years, we've been using Rust in the kernel. We've been trying to use it, writing some abstractions, writing drivers, and we've kind of learned what does it take to put Rust in the kernel. And it turns out that it doesn't just require Linux changes. It also requires some changes to the Rust language. And all of this culminated in summer last year when the Rust project announced the Rust project goals initiative. The goals initiative announced a list of goals that the Rust project wanted to put focus on and prioritize. And among them were some flagship goals, one of which is Rust for Linux. Or more specifically, the goal is to stabilize unstable language features that Linux needed so that Linux could use them without worrying that they would go away or change in future versions of the Rust language. But that was summer last year, and the idea is that it would last for 6 months. And it's now in the beginning of 2025, so it's a good time to look back at the past 6 months and say, well, what did we accomplish? And that's what my talk is about. I'll get right into it. So the one that most of you may have heard of, the one that has been the most publicized, is this issue with smart pointers. And so in Rust, we have these these types that are kind of like pointers, arc and box. And it turns out that in the kernel, for various reasons, we can't use the standard library versions of these types. So we have to make our own. But unfortunately, it turns out that they are special. They have special features that you can't do on your own outside of the standard library, at least not on stable Rust. And so the first one is didn't rate. If you have a box that you wrote on yourself, it would look like this. But the problem is, if you tried to use it with boxed-in trait, and many of you have probably done so with boxed-in future or boxed-in error, you're going to get an error if you're not using the one that comes with the standard library. And so what we added was the ability to make these smart pointers possible in your own code. And so we proposed this new feature for the Rust language called derive smart pointer. It did end up getting renamed before, in the end, but the point is, you add this macro to your Rust type, and now the dim trait feature of Rust is suddenly usable in the kernel. And I think there's an interesting principle here, because supporting dim trait with your own types in Rust has been stalled for years. There have been no progress on, and people have tried to stabilize it, and they run into major roadblocks. And so the way we were able to make progress on this issue in the Rust language was really by saying, okay, we can't stabilize the entire feature. So we stabilize a subset of it. And specifically what we did is this macro, normally a macro, it expands to code you could have written yourself. But this macro, you couldn't write the code that comes out of it yourself because it uses unstable features. But the macro itself is stable, or almost stable. And so this principle, I think, really is a good way to make progress on the really difficult language features. Another feature that I have to mention is this arbitrary self-types, which is also part of the smart pointer issue, which is another one that became part of the Rust for Linux project goal. Arbitrary self-types are, you may be familiar with, normally you write &self or &mute self in your Rust code, which means, you have a normal reference or a mutable reference to the value, but you could also imagine that actually I have a different kind of pointer. I have my custom pointer type to the value, and that's what this allows you to do. Okay, enough about that. So the next feature that Rust was missing, that Linux was using, is assembly goto. And I'm sure you hoped you would never hear those two words in the same sentence. Basically, it's a feature that lets you jump out of assembly directly into Rust code. And the kernel uses this for some interesting things. Let me show you. So let's say you had a global boolean called, is this fancy feature enabled? And you probably change it like really rarely, maybe like only at boot, or maybe like when the user changes some setting or whatever. The point is, you have this, if the feature is enabled, you use your special feature, and otherwise you use some fallback that may be slower or less featured. So in the kernel, they said, okay, using this if is slow. What if we could make it faster? And so what they essentially did, they introduced this thing called a static branch, where you have this assembly no-op instruction that does nothing. And then you call use fallback, and then you return, right? So you can see the way it is right now, the feature is disabled. But what they then do is that if I then come and I change this global boolean, they will go find this no-op machine instruction in the machine code, and while your machine is running, they'll change the assembly on your machine to replace it with a jump. And so in this way, the kernel is able to have if-elses that are never mispredicted. And of course, we unfortunately needed to use this in the Rust code too, and so we needed to make this possible to do in Rust as well. This is how it looks in Rust. So Rust already had the assembly macro, but the way we did it is we introduced this label thing that you could add to the thing. So the idea with the assembly macro is that you add a bunch of arguments, and we added a new argument type, which is a label, a block you can run, but only if the assembly block jumps to it. If the assembly block doesn't do anything, it's just going to fall through the bottom and call use fallback. Now, you may notice some interesting thing here, which is the assembly block is in an unsafe block, but the code in the label, it's unsafe because inline assembly is unsafe. But the code inside the label, you don't want that to inherit the unsafeness, which it would do by default since it's in an unsafe block. And in practice, these things are actually going to be admitted by a macro with user-provided code inside the label. And so what we ended up doing was to say, when you have a label that turns the unsafeness off, or into a safe scope, or however you want to call it, and so you have to use another unsafe block inside it. So that's kind of interesting because it's not something we have anywhere else in Rust. Another interesting thing is pointers to statics and constants, and it really comes down to, okay, let's talk a bit about global variables. A global variable, so you have, in this example, you have this thing, it's immutable, and it's a 10. So computing this function, get my global, at compile time is not a problem. I mean, it's going to be 20. All is good. But what if it is what was a mutable global? This raises some interesting questions, at least at compile time. Because if you have code at compile time that modifies the mutable global, what does that even mean? And so the Rust project decided, yeah, we don't want to answer this question. So if you touch a mutable global during compile time, that's an error. Fair enough. And that's also another case where it makes a lot of sense for it to be an error, and that's this extern C case where I have a global in some random C file called myglobal, and I want to access it. But when you're compiling the code, doing const evaluation, the C code is not there yet. You don't know what the value is, so trying to read it during compile time is not going to work for similar reasons. And so that's fine, but we do run into a problem. In the kernel, they use this concept of a vtable quite a lot. And so this is from the way the kernel implements files. And so if you have a file that's open on your Linux machine, internally it's going to have a pointer to this immutable global containing the file operations, which is a bunch of function pointers. That's C code you're looking. So if you're not familiar with C, this is the syntax for a function pointer. And so when you read on the file, inside the kernel, it's going to look up in this table of functions and call the read function. But the thing is, there's a little tricky field called owner. And this is, the purpose of owner is to handle what if you unload the driver while you have open files. If you did that, you're going to have a bad time. And so it uses this thing to keep track of how many open files does each driver have. And now we run into a problem in Rust, because the Rust equivalent for this is that we have this thing, the extern C global, and we put it into this vtable. But now there's a problem, because you're touching module from const evaluation. And that's not allowed, right, as we saw before. But there's not actually a problem here, because we're only taking a pointer to it. We're not actually reading the pointer during const evaluation. And so this didn't work. And, well, we fixed it. Okay, another thing is this maybe this. Okay, so the thing is, the entire goal of this project goal we announced, this collaboration between Rust for Linux and the Rust project, was making Rust work with Linux reliably. And what we've been doing is we've been stabilizing language features, but we also built Linux in the continuous integration for the Rust project. So every time someone makes a change to the Rust language, we're going to go in and build the kernel. And if it breaks, then we will detect it very early. And this will allow us to say, okay, maybe it was unintentional. Well, then you should go fix the change to the Rust compiler. But if it was intentional, it also allows us to go submit a fix to the kernel. And so that's kind of a thing, right? Because in principle, Linux doesn't necessarily need everything to be stable. I mean, it's great if it's stable, but the thing is, in Linux, we can submit fixes. We can change the code if something breaks. And so, if we know about these problems early, we set a fix, and we fix it. Yeah, and I think it's important to remember when you work on these things that stabilizing isn't necessarily the only option here. The Rust project could guarantee that, hey, this feature, we're not ready to stabilize it yet, but if we change it, we'll change it in a way so that you can fix the kernel. Like we won't just take the feature away, which they could do under the normal rules. Okay, so now I've told you a little bit about 2024. But this goal initiative, the idea is to have a rolling goal every 6 months with some selection of goals. And we have, in fact, decided to make Rust for Linux a goal in the next iteration as well. And so in 2024, we tackled a bunch of different language features. And they were, some of them are not completely stable yet, but we have solved the hard problems, and they will be stable soon. For example, the assembly one is still missing some documentation, but we've made a lot of progress. And so in 2025, what we're looking to do is, well, we took care of the language features, so now we look at tooling and compiler flags. And those are some things you see here. One thing that has been a big part of, let's say, the next iteration, we already started on this in 2024, actually, you can see in the date, but it's this idea of, essentially, it's solving some of the problems we have with compiler flags. Because it turns out that the kernel uses a bunch of obscure compiler flags that the Rust compiler didn't have or were very experimental. And the thing is, these compiler flags, in some sense, they're unsafe. Because, for example, there might be a compiler flag that changes how do you pass arguments from one function to another. And so if you have one piece of code compiled with that flag and another piece of code compiled without it, and you then call across the border, if they disagree on like how do you call the argument, so I think the first argument goes in this register, but the other one thinks it goes in another register. Like if you call there, you're gonna have a bad time. And so, in Rust, we want to make things safe. So what we ended up doing is essentially introduce a way to have these flags but still be safe. And so what we do is we detect mismatches between the flags, and then we fail if there is one. And then we have an unsafe allow API mismatch, which is an opt-out if you need that for some reason. Another interesting thing is, it turns out that in the kernel, we don't use cargo. We use make. And so that means that, when you use cargo, it's purpose-built for Rust, so it knows how to build Rust code. But in make, when the Rust compiler builds something, it might touch a bunch of different files, and if you change any of them, then you need to rebuild the project. And so the Rust compiler needs to output this dependency information in a way that make can understand them. And there is this -set binary deb info flag. But we would really like to stabilize this so that we actually have that we know it works and that we know the format it's not going to change. And we also have some other tooling. Rust is very famous for having really good documentation testing. And we would like to have this in the kernel too, and we do. But it's currently pretty hacky the way we actually get where are the tests out from the Rust code and then pass it to the kernel's testing framework. And so we would like to have the Rust documentation tooling to have a more established way of providing this information of what are the documentation tests. And then there are some with Clippy. There are some things with, we support a range of compiler versions. And the thing is, what if you have a Clippy lint that only exists on the new compilers, and then you mention it in the configuration on an old compiler? There are some things here that need to be worked out. So, yeah, the conclusion is essentially, in 2024, we tackled, this is the takeaway I want to give you. In 2024, we looked at what are the language features, and we solved them, or at least we answered the hard questions. And there are still some things we need to fix, but they are very close to stabilization now, which was definitely not the case a year ago. And in 2025, we are now able to change our focus to the compiler tooling and compiler flags, and to work on those instead. And in my other talks on Rust for Linux, I've said, if you want to contribute, you can contribute to the kernel. But since this talk is about the Rust project goals, about improving the Rust language to be a better fit for the kernel, I'd like to mention that one way you could help out the Rust for Linux project is by helping us stabilize unstable features, or even add new features to the language that would make Rust more convenient in the kernel. One thing we have to remember is that the kernel has a lot of C developers, and kernel Rust is going to be their first experience with Rust. And so we want them to have a relatively good experience because, the kernel is exactly the kind of low-level thing we want Rust to be good at. And so we would also like to make changes to the Rust language that make the experience more nicer, even if we have ways to work around it today. One example of that is this thing called field projections, which is currently an open RFC, to add a new feature to the Rust language to make working with, there's both pinning, which is very important in the kernel, but also something called RCU, which is also interesting, where we also think that field projection will make things a lot more convenient. Yeah, so I hope you will contribute to one of these. And also, it's important to mention GCC. That's also going to be important in the long term for Rust in the kernel, because, well, not everybody builds it with Clang. So that's really all I had. So thank you for coming. Let's do some questions. Yeah?
Most of the contributions that you mentioned were to drivers. I was just wondering whether there is also an intention to put Rust into some of the more like core parts of the Linux kernel.
So the Rust for Linux project definitely wants, like, there's no rule that we can only go in leaf modules or drivers, so to say. And that's definitely a place we want to be. But the reason we're starting in drivers and such is actually because of this thing with GCC. And I guess one way you could go about it would be to have dual implementations of a core part of the kernel in C and Rust. But we do try to avoid this. We would rather write new stuff, or if we rewrite something, we would rather delete the old version, so to say. So, yeah, we definitely want to do that.
So, touching over here, sorry, I already got the microphone. Thanks. It touches on the other question a little bit. It's more of a non-technical question. You already shared that post by Greg KH, which was very encouraging. But there has recently been some some drama around Rust in Linux. And although there seems to be some encouraging openness to it from key people, there is also some pushbacks, particularly from the maintainer of the DMA subsystem. How do you see that going forward? I mean, is there some reconciliation possible? There are very, very strong opinions about this.
Yeah, so you mentioned the DMA maintainer, Christoph Helwig, and let's say we knew that it was coming with Christoph, and because we knew he was against Rust, so the current controversy was not a surprise in that way. I think the takeaway you should have here is that, things are still being discussed on the mailing list, but I think things are going to be fine, and we have it under control more or less. I think that's the takeaway you should have here. So don't be worried that the project is dead because of this. I wouldn't be worried about that. So where is the mic now?
Yeah, thanks for the talk. I wanted to ask a more practical question around, is Rust Analyzer happy, given that you're using Make? And generally, how does it work? Because I guess a lot of the tools in the Rust ecosystem assume cargo and that setup.
So Rust Analyzer actually does not assume cargo. Concretely, what we're doing is that we have a make target called, I think it's just make Rust Analyzer, which generates a file called rustproject.toml, I think, that Rust Analyzer uses to know where are all of the pieces of Rust code and how do they depend on each other. And so it actually works quite well. There have been some tweaks recently to say, related to the where do you find the core library and so on. But yeah, it works reasonably well, I think. Now, of course, the thing with cargo is kind of interesting because in the Rust Analyzer case, we're good. We don't actually need cargo for this to work. But there have been some other tools because we use bindgen to go from C code to Rust, C headers to Rust. Let's say not headers, but headers. But going the other way uses a tool called cbindgen. And this tool does, in fact, require cargo. And so we don't have that functionality in the kernel. If you're going the other way, you have to write your signature twice in both languages. Any other questions? There are multiple ones over here. I see the mic is coming.
How do you, thank you for the talk. How do you handle dependencies? Like, can you, is there a process to choose like crates? I guess things like has to be nested, or is there a process to decide what dependencies you can use?
So on the topic of dependencies, essentially the situation is that like we don't like download dependencies via cargo. They have to be in the kernel tree. And so, with the exception of the standard library. And so, right now, you use very few dependencies, let's say. The only dependency we really have is, it was actually some code, it's called pininit, which is some code we came up with for in-place initialization. So it actually started in the kernel, so to say, but we're moving that into a separate crate on crates.io and also extracting it out to be like a separate directory and a separate crate in the kernel so that we have the same code in both places. But yeah, and we would also like to have syn as well. And of course with syn, that's for proc macros that runs on the host. And so there you don't require no STD. So for proc macros, the possibilities are greater. But I still think they would need to either be shipped with the compiler or be in the kernel tree. There was another question over there.
With the addition of Rust in the kernel, is there any concerns about limiting the targets that you could have for the kernel now? Because now we're stuck to having targets defined that are available for Rust.
So was the question about like architectures or editions?
Architectures.
Architectures. So the first architecture that was added to the kernel was x86. And we've later added ARM, and I think RISC-V is also there now. But it is definitely the case that if you want to add a new architecture, like you don't just get all of the architectures for free. And so, yeah, you have to add them. And there's also stuff on like you saw some inline assembly, right? We also, that's architecture dependent, so you probably need to modify the code related to that to add a new architecture. But yeah, as it is right now, we could support any architecture that LLVM supports. And of course, there are also these 2 different GCC projects that are adding support for GCC, which would make all of these architectures that are only available to GCC available to us. And I think that Rust-C, CodeGen, GCC can already compile the kernel, as far as I've heard. So that is super cool, though it is still very experimental, I think. And that's another good place to contribute if you are interested in that. I hope that answers your question.
Yeah, that's great. Thank you. Yep.
How much work is left on the Rust language side? You mentioned like a bunch of stuff that was done in 2024, but is there anything left that's blocking the kernel work at all?
Well, so there are some of these that we solved the hard problems, but there are still some missing things we need to do before they are fully stabilized. So there's of course that. And then there's a really, really long list of compiler flags. And so that's also going to require a bunch of work. And I think the situation with compiler flags is that on that front, we will never truly get to, let's say, stable. in the sense that there are going to come in new compiler flags sometimes, right? Because maybe some architecture decides, hey, we have this new feature, and then they add a flag to Clang, and then we add it to Rust-C, and then we want to start using it in the kernel. But again, if you go back to this thing I was talking about, like, you don't necessarily need to be fully 100% unstable Rust. You just need it to be stable, like, enough, let's say. And so, yeah, but I think the next big one is going to be compiler flags.
And if you, like, even using unstable, there's like nothing that's actually blocking them from using Rust.
Well, I mean, it's working. I've been using, I wrote this binder driver in Rust a while ago, and it's been working on real phones for over a year.
Thanks.
With unstable features.
I'm curious how much of the feature set of sort of, if you're a user space application developer today writing Rust, is a very similar experience now working at the kernel level, or is there a lot of features that you can't rely on, like async and...
Well, so async is actually kind of interesting because async doesn't actually require allocation. So you could use it in the kernel. And I think there was actually an example implementation from Wetson using async with the kernel work queue as a runtime. But other than that, oops, I clicked something. Okay. Yes, there are a lot of features we can't use. And it has to do with, well, we used to use, like, even alloc, the allocation part of the standard library. We don't use that anymore. We used to, but allocation works in an interesting way in the kernel. You have to pass these extra flags every time you allocate memory. And in the end, what worked best for us was just to make our own allocation library. And well, it's missing a bunch of stuff that the standard library allocation library has. We don't have the B tree, and yeah, so in that sense, there is missing quite a lot of stuff. So kernel Rust is not the same as user space Rust, I would say. Do I see any questions? Oh, there.
Sorry, last one. Is there any recommended starting material to learn about getting involved with this kind of work?
Rustforlinux.com.
Okay.
We also have a Zulip channel, which you will find a link to on rustforlinux.com, where you can chat with the project members.
So that's quite a few things that have happened to Rust to make it compatible with Linux. Has anything happened in Linux to make it more friendly to, say, Rust?
Good question. So another change that we were looking into making for Rust. So you may have so there's this feature in Rust called track caller, which essentially, if there's a crash, you get the crash location, like, not inside the unwrap function, but you get that where you called unwrap. And the way this code works is that, well, you get a string, like there's this thing that will give you the string of the location. But the string is not null terminated. And so I can't actually pass the string into the kernel's printing infrastructure to print the location string. And so we've been trying to make some changes to the Rust language to make it null terminated. I'm not sure whether we will end up doing that or not. But for now, we had to update the kernel to use a null terminate, to accept a length for the string. Yeah, and this is actually also something Greg has been talking about several times, which is, like, if you're doing something really ugly on the Rust side, well, maybe we should go change the C side and improve the C side probably to make this better. Yeah. I hope that answers your question. Any more?
We've still got time for questions, so feel free.
We have done there.
Thank you for the talk. What's the relationship between the Rust for Linux project, the Rust Foundation, and the Linux Foundation? And then obviously you have sponsors for all of those big projects who are kind of putting a lot of money into this and care about Linux working and trying to make it safer. Can you maybe just explain, that kind of team side of it and what the incentives and pressures on the project are?
So I would say Rust for Linux, like that project, is more of part of the Linux kernel. Like it's not a Rust project, let's say. It's a Linux kernel project, so to say. And so being part of the Linux kernel, you mentioned the Rust Foundation, it's not like, but we did set up this collaboration between the Rust project and the Rust for Linux group, which started about a year ago, where we had these regular meetings every other week to work together in the projects. And this also kind of is what ended up culminating in this project goals thing. And we decided to make this bi-weekly meeting into part of this goal. I don't know if that answered your question. All right.
Yeah, right at the back.
Actually, my second question, sorry. One thing that people have been talking about is lack of maintainers. A lot of open source volunteers overworked, trying to get young blood in particularly things like Linux kernel development. And to what extent has the adoption of Rust as a new modern popular language in Linux, or at least the prospect of it, led to engagement from possible new maintainers? What is your experience in that?
Well, I will start with saying that the average age in the Rust for Linux group is smaller than the average age in the Linux project as a whole. You will actually find that for some of the subsystems, like when we go to a subsystem and say, hey, we have these Rust bindings, sometimes the subsystems have asked for, can we have a maintainer also for our subsystem, or like for the Rust part? And so there have really been these people who come and work on the Rust side, and they become, let's say, part maintainers of these subsystems as well. And as is typical for the Linux kernel, most people who work on it do that job. Right? It's mostly not hobbyists that work on the kernel. And that is also true on the Rust for Linux side. I do it as part of my job at Google. There's also Andreas from Samsung, Patrun from Microsoft. So, yeah. But that is really no different between the Rust project and the rest of the kernel. Any other? Oh, we have one more.
Thank you for the talk. What other applications for these features do you think there could be?
For which features?
For the things that you guys stabilized, well, not stabilized, just made in the compiler.
So I think that some of these features will, we're doing it for the Linux kernel, but it's not just useful for us. For one, many of these compiler flags are actually useful for embedded systems as well, other operating systems. And also, if you go back to this arc and box issue I talked about, well, I mean, that really applies to anyone who wants to write their own smart pointer. If you look at a crate like, I don't know, Bumbalo, the bump allocator, that also has a box, a custom box, which doesn't work with didn't trait because it's unstable. And so this work we've been doing really, also benefits these crates that want to do these kinds of things. Arbitrary self-types, so that was already in the works before it became part of this project. But that's also motivated by C++ interop. They want to, they have these large C++ code bases that they want Rust in, and they want to have these C++ pointers or whatever that, make interop more nice. And arbitrary self-types is also helping with that.
Any more questions? Okay, going once. All right, please give Alice a massive hand.